I'm going to follow a bit on the previous talk by Professor Sotelo, and I'm going to be talking about materials that have some thermal properties that are very interesting. These are not going to be thermoelectrics, are going to be called caloric materials, and I will tell you a bit more in a second. The work I'm going to present is done in collaboration with colleagues here in Cambridge, a very good friend of mine in Costa Rica, and also a very good collaborator in Japan. Right. So, when normally we talk about advanced functional materials, we tend to think of materials that have a phase transition. And the interest of having materials with phase transitions is that normally when you have a material that is close to a phase transition, if you can drive it somehow with temperature or with a magnetic field, with an electric field, normally these materials give you some kind of new functionality that you can hope then you can exploit in applications. When you talk about phase transitions, normally you talk about two different types. So there are first order phase transitions and second order phase transitions. So these are sketched here on the top left. So here I'm sketching order parameter X. So X will be magnetization in a magnetic material. It will be polarization in a ferroelectric. And then if you plot it as a function of temperature, the difference between a first order and a second order material is that in a first order material, which here is shown in pink, the transition is very sharp. So you go from one phase to another phase in a very sharp manner, whereas a second order material has a transition that is much more continuous and it occurs over a broad temperature range. You can make these changes in the order parameter using temperature, and normally, and more interestingly, you can also control these changes with an external field. And in that case, what you look is a plot that looks a bit like this one here on the top, the bottom left, where you have order parameter X as a function of applied field. So for instance, if X is magnetization, Y will be magnetic field. And if X is polarization, Y will be electric field. And again, you can then control the order parameter. And the nice thing is that if the transition is first order, then by applying a relatively small field, you can change the material from having a zero or very small order parameter to a very high order parameter. And this is where you can start thinking about making sensors, actuators, or other type of devices. Also, interestingly, many materials actually have multiple functional properties, and a typical example are multiferroics, where, for instance, you can have magnetization and ferroelectric polarization in the same material. And this kind of multifunctionality is very interesting because, in principle, then you can find new applications. So today I'm going to be focused on one type of applications, and just to let you know, so the motivation that we have is basically driven by scientific curiosity. So we are interested in the properties of the materials, but also many of these materials have potentially applications in sustainable energy, and I will describe some now. So when we talk about applications of these materials, there are many, depending on the type of material that you have. If you have a metallic alloy, or you have a ferroelectric ceramic, or a polymer. So these are some of the applications that are typically listed as applications of functional materials. So you can have magnetic shear memory effect, you can have piezoelectric sensors, you can have thermal storage devices. And I'm going to concentrate on caloric cooling. And I will tell you in a second what these caloric materials and these caloric applications are. So caloric materials are materials that can change the temperature when you apply an external field. The most famous ones are magnetocalorics, where you apply a magnetic field, and then you can drive thermal changes in the magnetic material. These materials were discovered more than 150 years ago. They are very well known. And they are actually used in many research labs in order to achieve ultra-low temperatures. So many of you, of course, are aware of this magnetic. Basically, this is the magnetization cooling technique, where you take normally a paramagnetic salt at low temperatures, and then you remove a magnetic field, and then you get some extra cooling, so you can explore materials in the medical region. In the 70s, after some work done by Gerald Brown in NASA, these magnetocaloric materials were also proposed for cooling applications at room temperature. So the idea was to make a fridge using a magnetic material. And this has the benefit that, as you may know, in order to achieve cooling, if you look at your fridge or your air conditioning system, normally what we do is we take a gas and then we compress it. And when we compress it, we drive a transition, which is first order, from a gas state to a liquid state, and the fluid gets hot. And then when you expand the liquid, the opposite transition happens. So you go from liquid to gas, and then the fluid gets cold. And this is actually what you use. So you make a cycle continuously, and then you can cool down your food, you can cool down your building. And this is what you use in vapor compression, which is a technology that has been around for more than 100 years. It's very well established, it works very well. But as you will know, the gases that we use for vapor compression are harmful for the environment. They contribute dramatically to the greenhouse effect. So for many years now, there's been interest in looking at materials, solid materials that can provide cooling. And for instance, thermoelectrics that was just presented before are an example of materials that can provide cooling if you apply a voltage to them. The issue with thermoelectrics, and they work fantastically well, and we use them in the lab to control temperature of experimental systems all the time, is that the efficiency, as was discussed before, is relatively low. So in calorics, or caloric materials, what you want to do is you want to drive a phase transition. So in a way, this is analogous to vapor compression, but instead of driving a transition between a gas phase and a liquid phase, you drive a transition between two different solid states. And for the case of magnetocalorics, normally this is a transition from a paramagnetic state to a ferromagnetic state. And when this happens, the material gets hot, and when you remove the field, the material gets cold. So you can also think about making cycles. Now, in terms of magnetocalorics, if you want to make an efficient application, you need to use a permanent magnet. And typical permanent magnets that are not really huge and not very expensive, normally give you 1 Tesla, 1.5 Tesla magnetic field, which means that the best materials, the best magnetocaloric materials, normally they give you a temperature change in the region of 3 degrees. So it's relatively small, so it's not so easy to make an application. This is why actually there's been a lot of interest, especially since 2006, in looking at electrocaloric materials. So here you also want to drive a phase transition in a solid material, but in this case you use an electric field. And this has the advantage that applying an electric field is very easy and it's very cheap. Now, in this case, the phase transition is normally between a paraelectric state and a ferroelectric state. So you normally use ferroelectric materials. And then there are other two types of materials that I'm not going to cover for the sake of time. You can drive materials using uniaxial forces, and then they are called elastocalorics, and then you can also use hydrostatic pressure, and they are called barocalorics. If somebody is interested, here are a few reviews that we published in the last few years, so you can find lots of information in there. And just before I move into some experimental results, I just want to show you a video, and let me know if it doesn't work. Hopefully it does. So this is a video of a balloon, just a normal party balloon. So you will see my hands coming in a second. So that's a balloon here, and these are my hands. So you will see when I stretch it very quickly, the balloon gets hot. And hot in this scale is white color. Then I can wait until the material recovers the original temperature, which in this color scale is purple. And when I let the force go, you will see that the polymer or the balloon is going to get very cold. It will get black. So this is an example of an elastocaloric material that you can drive with your hands. And it's just a balloon. So if you want to do this experiment at home, it's very easy. Just take the balloon. You don't need an infrared camera. Just put it in contact with your lips, which is the best thermometer that you have in your body, and then just apply force and remove force, and you will see this heating and cooling. So this is how they work. And this works because in this case the balloon is a polymer, and when you apply the stress, what you do is you drive a transition between an amorphous phase and a crystalline phase, and this gives you this heating and cooling. But of course, we don't use balloons because the temperature changes are not that large for applications, so we are interested in other materials. And today, for the sake of time, I'm going to be concentrating on one particular type of material, and in particular, electrocaloric material. In electrocalorics, as I said, you have the advantage that you can use an electric field, and this is very convenient because then you don't need to use an expensive permanent magnet or a large motor to apply a big force. They've been investigated now for many, many years, but historically, these electrocaloric effects were always very small. And why is that? So if you look at the graph here on the left, here you have the electrocaloric temperature change, the delta T, as a function of temperature when you apply field to this ferroelectric oxide here. And you can see that the largest effect is around 2.5 Kelvin, right? So not that large. So the question is, why don't you get larger effects? The reason you don't get larger effects is that in electrocalorics, the temperature change that you can get is proportional to the maximum electric field that you can apply. And as you may know, in any dielectric material, in any insulator, you can apply electric field larger and larger, but at some point you are going to break down the dielectric, and then you will start having conduction. And when this happens, then the material doesn't work anymore. So the challenge with electrocalorics was always how can we apply a larger and larger field, right? With ceramics, basically this was kind of the state-of-the-art maximum field that you can apply, and this was the maximum temperature change that you can get. But then in 2006, my colleague Neil Mathor here in Cambridge basically proposed to use thin films. And why is that? It's because in thin films, it's known that the breakdown field is inversely proportional to the thickness of the material, which means that the thinner the ferroelectric material, the bigger the electric field that you can apply. And that means that the larger electrocaloric effect you will have. So in 2006, they published a paper where they show that by looking at thin films of this ferroelectric material, let's call it titanate, they were able to apply order of magnitude larger electric fields, so in this case nearly 500 kilowatts per centimeter, and the temperature change was also one order of magnitude larger. So they were able to get around 12 degrees. And this is when things start getting interesting, because if you have a material with a temperature change of plus minus 10 degrees, you can start thinking making some application. Now the challenge then was that this film was 300 nanometer thick, and if you have something that is very thin, the thermal mass is very small, so it's very difficult to cool anything down, right? You cannot expect to cool down a can of Coke, let's say, using a 300 nanometer film, because the thermal mass is just too small. So a solution, or a suggestion, came by using multi-layers of this material. So the idea is taking thin films, so you can have very large effects, and then you stack many, one on top of each other, so you have enough thermal mass to make basically a cooling system. This actually is well known in electronics. These devices are called multi-layer capacitors. Any of your computers, your cell phones have actually hundreds of these multi-layer capacitors. They are normally used for storing charge. Also because of this idea of having many layers, so you can store more charge in a smaller volume. And these multi-layer capacitors, in a way, have the best of bulk and thin films. So they can have large electrocaloric effects. You can use small voltages because the electric field is voltage divided by thickness. So if the layers are thin, you can use a small voltage and get a big electric field. Because you have all these layers intercalated with metallic electrodes, you can actually have good thermal transfer. And then because you can actually make these multi-layer capacitors very big, so this one, for instance, is the typical one that you have in your computer. So you see that they are 1 millimeter. The size is in the region of millimeters. They can have large thermal masses. So a few years ago, we were trying to improve the electrocaloric performance of these capacitors, because traditionally they were made of conventional ferroelectrics. So for instance, in the previous slide, the one that I showed you is made of barium titanate, which is perhaps the most famous ferroelectric material. But barium titanate is not a very good electrocaloric material. And then other works that were published over the years were basically based on barium titanate, BTO, lead magnesium niobate doped with lead titanate, so this is pure NPT, or lead magnesium hybrid. And you can see that basically all of them, the performance at most was around 2.5 degrees, right? So we were interested in trying to see if by replacing these electrocaloric materials with better electrocaloric materials, we could make multi-layer capacitors with much better electrocaloric performance. And Also with the idea that actually these multi-layer capacitors, even though the performance is not as good as could be, they've been actually used in a number of prototypes, of cooling prototypes. Right, so the material that we chose was lattice scandium tantalate. So this is a perovskite, so it's similar to barium titanate. But you have this half doping of scandium and tantalum, and actually when you order this material almost fully, so you have scandium and tantalum in neighboring sites, this material actually is a really excellent insulator, which means that you can apply a very big electric field, and then potentially you can also have a very large electrocaloric effect. And these materials actually were suggested in Russia, well, back then was the USSR, in the 80s and the 90s, and they show good performance. So you see this is a ceramic sample, and they were able to measure around 1.6, 1.7 Kelvin under 25 kilowatt per centimeter. So what we did is with our collaborator Sakio Hirose in Murata, which is one of the largest manufacturers of multi-layer capacitors, we started this project of making these multi-layer capacitors out of PST. The capacitors that I'm going to show you today, they have 19 layers of PST. They were 0.84 millimeters thick in total, and they were highly ordered. So the ordering we tested with X-rays, so you can do X-rays, and then by comparing the intensity of the superstructure peak compared to the standard peak, you can see how well ordered the material is, and we got almost 100% ordering, which is really good. Then we measured the ferroelectric properties to see if the material was behaving well electrically, and we got very nice ferroelectric loops. So this is polarization as a function of electric field. So you can see in the high temperature phase, which is, for instance, this red data, the material is ferroelectric, and then when you cool down, the material becomes ferroelectric. So this black data. And in between, you can see actually, for instance, if you look at the purple, when you are close to the transition, you can drive the material from being paraelectric to ferroelectric with an electric field. So this is an example of a field-driven first-order transition, which, as I said, is potentially very good very interesting for the electrochemics. So then what we did is we tested the thermal properties of these materials, the caloric effects. So we did this using a thermocouple that was on top of the capacitor, and also using one of the infrared cameras that we have. And then we got a series of results. So first, let me show you what we call the indirect method. So this is a way of calculating the electrocaloric response that you expect just using polarization data as a function of field and temperature, and then thermodynamic relationships. And this already was looking very promising because it showed us that you can actually drive the transition with electric field in a broad temperature range. So this is indicated by this black line that separates the paraelectric phase, which is blue, from the ferroelectric phase, which is red. And this translates into a large electrocaloric response. And if you actually measure it directly with the thermocouple and the infrared camera, we were actually able to measure thermal changes up to 5.5 Kelvin, which is pretty, it's very large. You can see that it's almost doubling, it's actually doubling what was known before. And this value of 5.5 degrees is particularly interesting. So this is an example of the thermocouple data in black and the infrared camera data in purple. Then you can make these measurements as a function of temperature, so you can get the thermal response as a function of temperature. You see the maximum that we got was around 5.5 degrees, and as I was saying, this particular value is interesting because if you compare this electrocaloric material with the most famous magnetocaloric material that is used in prototypes nowadays, which is gadolinium, you can see that gadolinium in 1.5 Tesla, which is a typical field from a permanent magnet, shows a temperature change that is in the region of 2.5 degrees, right? And this actually has been used in many prototypes that are showing good performance. So the excitement came by the fact that in these multi-layer capacitors of PST, you can actually get twice the temperature change, also over a very broad temperature range. Because if the material is only operating in a very narrow temperature range, for applications again is a problem. So you can see the gadolinium has a relatively narrow peak, whereas the PST has a really broad peak, which is also potentially very interesting for applications. So we actually communicated this 3 years ago now in Nature, and these MLCs actually now have been used in prototypes, which have been also published in both journals. So it's all looking very promising. And just to finish, I wanted to say that in general, these functional materials that have phase transitions are very interesting for many applications. And for calorics in particular, whenever you have materials that have a strong coupling between the electrical and thermal properties, or the structural and the thermal properties, and so on, these materials that have multiple couplings can be very interesting for calorics, and there are many materials to investigate. So this is, there are extremely, the playground for this research is very fertile. It's sort of like gaining momentum now, so it's a good time to investigate materials for calorics, and I will welcome you to come and join the community. And then just to finalize, in case you are not familiar with these caloric materials, I give you the references that I mentioned before. So we published a review paper on all the different types of caloric materials in 2014, and then just last November we published a second review with an update on these materials, and I give the references there, and I'm very happy to take any questions. Thank you very much.
With these materials, these caloric materials, be complementary to what we had, for example, in the last talk from Andres regarding their applications, for example, with respect to thermoelectric materials?
Yes, they are similar and different in a way, because with thermoelectrics you can actually get cooling and heating, and you can also harvest energy, right? These materials, these caloric materials, they can also be used for cooling and heating or for energy harvesting. But I think they are complementary in the sense that in thermoelectrics, you don't drive a transition, so you just use the fact that electrons and holes can carry heat with them, so you can use them for pumping heat. In these caloric materials, you exploit a phase transition, so it's a different phenomena. But yeah, I think something that is very important is that we need to find a solution for heating and cooling, in particular, that is low carbon, right? Because vapor compression is very harmful for the environment, and you may not be aware, but 40% of the total CO2 emissions, for instance, in the UK, 40 comes from heating and cooling alone. So if we want to decarbonize society, heating and cooling needs to be decarbonized, and I think that means that we need to use a solid material instead of a fluid. Now, if this is going to come from calorics or from thermoelectrics or combination of both or some other type of effect and material, I don't know yet. But it's something that is very important, because we need to find a solution to reduce the carbon emissions associated with cooling and heating. And it's something that, thankfully now is becoming more important, because I think it's actually one of the big challenges that we have. And this is why, as I said, I will welcome everyone to come and join the community, not only calorics, but like thermal properties in general, because decarbonizing cooling and heating is going to be very important in the next 10 years.
Yes, yes, and thank you. In any case, there's, I guess, complementarity has always been the case for most technologies and most materials, right? So that it's very nice to have different options for which may be optimum in different applications in any case, right? So this is, I think this is very interesting.
It's also good, like, for instance, having sessions like this one today, where you can actually see like thermoelectrics and calorics together, because I think also sharing knowledge within the different communities is going to be very important.
Yes, definitely, and there's always a link between all these energy solutions, I would say, right? So I think that's what makes it very interesting. So thanks very much.